Okay, as I said, we are going to record this, and if someone has any problem, the person can let us know, and maybe we are going to stop recording. Now we are going to start by the first problem, or the first assignment that I said to send to us. I hope that you have it, or maybe Aisha can send it again, or I'm going to write everything. Maybe I'm going to write everything, and we are going to solve just the first part, because the first part is function analysis and the second part is complex analysis. But I heard that you didn't reach complex analysis already, so we are going to do only the functional analysis part. So functional analysis. Academy. You cannot watch?
No, we can see your screen.
You can see, but it's like there's someone who cannot see. Academy year 2021-2022, session of the 18th of July 2022. So the question is to check for the following function. Sequence of functions. If the monotone convergence theorem can be applied. So I hope that you know the monotone convergence theorem, or the Beppo-Levi convergence theorem. If you don't know it, I'm going to state it. So let me state it before. Monotone convergence theorem, or Beppo-Levi convergence theorem. So I will state it by my own way. Maybe it is almost the same like what you did during your lecture. So let Fk be a sequence of positive functions. Be a sequence of positive measurable function. So when I put 0 plus infinity, it means that the sequence is positive. Now be a sequence of measurable functions. Assume. Now, when you have a sequence of measurable functions, positives, now assume that the sequence is an increasing sequence. So we have to assume that increasing sequence means that f of kx is less than f of k plus 1 of x. So assume that we have an increasing sequence. So almost everywhere. When you have this, when you have a sequence of positive measurable functions, and the sequence, it is an increasing sequence, then there exists a measurable function f defined from Rn to 0 plus infinity, measurable such that the sequence of function fk converge almost everywhere to f. So fk converge almost everywhere to f. And the limit of the integral of the sequence fk when k tends to plus infinity equal to the integral of fx dx. So this is what again? This is just to say that we can switch the position of the integral of the limit, because this one is the integral of the limit of the sequence fk of x dx. So the Beppo-Levi theorem or the monotone convergence theorem is just to help us to switch the position of the limit and the integral. So when you are asked to compute the limit of the integral of a sequence, you can try to check if your sequence satisfies the Beppo-Levi theorem or the monotone convergence theorem. That is what you have to check. And monotone is the concept of monotony comes from here. Monotone means to be increased or decreased. So, and here the monotonicity is about increasing. And this theorem is the same like the Lebesgue dominated convergence theorem, but this one is more easier. Now this is the theorem. So we are going to take the different sequence of functions that were given to check if each of them satisfy the monotone convergence theorem. And if it is the case, we are going to compute the limit of the integral. Otherwise, we are not going to compute, or maybe we are going to compute, but we are going to know that we can compute the limit of the integral, but not because of this theorem. So the first sequence, I have fn from 0, 1 to r. So n is an integer. Now, fn of x is what? Is the cosine of x over n. So we have to check all the hypotheses of the theorem. So fn, is it a sequence of measurable functions? Yes. Why? Because this sequence is continuous. And when you are continuous, you are measurable. So the continuity is stronger than the measurability. So when you are continuous, you are measurable. But it doesn't mean that when you are measurable, you are continuous. So it is very easy. So every time when you want to check that if your function or a sequence of functions is measurable, you just have to check if your sequence of functions or if your function is just continuous. And it is the case here. So this sequence is measurable. Now, you have to check the monotonicity. Is it increasing or decreasing? So if it is increasing, it is good. But if it is not increasing, so if it is decreasing or if you cannot find the monotonicity because you know that there are some functions that you don't know if the function is increasing or decreasing, then it means that we cannot apply the theorem. So to apply the theorem, you have to be sure that the sequence of function is increasing. Now to check it, you just have to compute what? It is increased in terms of sequence. So in terms of n, it's not in terms of x. So you have to make the difference. they say that increasing sequence, not increasing function, increasing sequence with respect to n, the index n. So you know how to check it. So you compute fn plus 1 of x. This is cosine x over ns over n plus 1 with x between 0 and 1. So this is fn plus 1. We have to compare this with fn. We know that 1 over n plus 1 is less than 1 over n for all n greater than 1. You know. Now, if you multiply both sides by cosine x, so both sides cosine x, yeah, cosine x is positive. So we can multiply and nothing is going to change. So we have what? Fn plus 1 of x less than f upon x. So here we have a decreasing sequence. And we were supposed to have an increased sequence. So this is what? This is Fn of x greater than ff plus 1. Or we are not looking for this. This does not satisfy this one. This condition is not satisfied. Then we cannot apply then we cannot apply the monotone convergence theorem or the Beppo-Levi convergence theorem. Since that we have a decreasing sequence of function. But the thing is that, is it possible to compute this integral even without using the monotone convergence theorem? Is it possible to compute it without using the monotone convergence theorem? In this case, it is possible. Why is it possible? Because you can compute this integral. And in most of the case, we use this theorem because it is difficult to compute this integral. And we are looking for a simpler way to compute it. So by switching the integral and the limit, now to use now the integral of the limit of the sequence. But to use it, we have to be sure that we can apply the Beppo-Levi convergence theorem or the Lebesgue-dominated theorem. But in this case, even without this theorem, we can still compute it. Why? We can compute the integral of this function. What is the integral of this sequence of function? So it's just the integral of cosine x over n dx. And most of you know this one. So this is just 1 over n sine x 0 to 1, which is sine 1 over n. So it means that the limit of this of fn of the integral of fn z x when n tends to plus infinity is just the limit of sine 1 over n when n tends to plus infinity, which is 0. So you see that this theorem was not very useful, but we can still compute this limit. The question was if it can be applied, compute the limit. So I don't know what the lecture was expected, because we can still compute this limit, but without applying the monotone convergence theorem. So it doesn't matter. Now we are going to take the second one. You have the sequence fn.
Scusami.
Yeah.
Hi, Romaric.
Yeah, hello.
Did you just assume about the cosine function? Did you assume that it's non-negative?
Yeah, we are going to assume that between 0 and 1, the cosine is positive. I don't think that's negative. It's right. It is very difficult to see it.
But it's
Yeah.
oscillating,
Yeah.
so it can be anything.
Yeah, maybe you can take a calculator and you compute the value of cosine between 0 and 1. Normally, we know that the cosine function is positive between minus pi over 2, pi over 2, or between pi over 2, 3 pi over 2. Now, if we assume that the interval 0, 1 is between, I just assume that this one is between this interval in 0 to pi. So I'm taking all the trigonometric circle. So if this is true, it doesn't matter because the cosine is positive here. It is like this. So you have 3 pi over 2 here. You have pi over 2. Or if you are using minus pi, you can put minus pi over 2 here. This is 0 here. So this is 0 or 2 pi, according to what you want. So I guess that when we say 0 to 1, I assume that we are somewhere. Maybe 1 is somewhere, I don't know. So it means that the cosine is positive here, right? And if the cosine is negative, yeah, it means that we can apply, because if cosine is negative, if the cosine is negative here, it means that we are going to switch the position. And we are going to have now an increasing sequence. And it means that it will be possible to apply the Beppo-Levi theorem. And by the end of the day, we are going to have the same result, because the limit of f here is 0. So we are going to have the limit of the integral of fn equal to the integral of 0, which is 0. But cosine x is positive. If cosine x was negative, you will have something like this. If cosine was negative, I say that if cosine was negative, it will be like this. And this changed everything, because we are going to have now fn of x less than fn of x. And this is an increasing sequence if cosine x is negative. But I think it's not the case here. But maybe we can check. I don't know if someone can check. But cosine of 0 is what? Is 1, right? So you understood. Obviously, if cosine is negative, you know how you are going to do. So it's not difficult. It's right. It is a little bit weird because now down they put the absolute values of on cosine. I don't know, maybe the goal was to confuse the students or how. Since that cosine is positive, I don't see why we need to put the absolute value again here because it will be the same problem as the previous one. Okay. So the second one that we are not going to do anything since that it is similar to what we previously did. Now it is written this, yeah, this one. So since then and we have the previous result. Please take time to check very well the sign of cosine. We are not going to check it here. We are very soon you can check it. So the goal here is just to explain everything, how you can use the monotone convergence theorem. Now we have fn defined from 0, 1 to r. So this one is a piecewise function that we are going to define. It is an integer. Now what is fn of x? Fn of x is a piecewise function. So it is 1 here if x is between k over 2n, k plus 1 over 2n. Where k, it is an odd number between 1 and 2 power n. And it is 0 otherwise. So obviously, if k is odd, we know that k cannot take the value 0. K can take 1, 3, up to 2n minus 1, because even 2 power n is even. So, and the previous number between 2 and 2 power n is 2 power n minus 1. So normally k goes from 1 to 2 power n minus 1. And we know that if you have maybe a sequence of number, maybe from 0 to, if you have a sequence of number from 0 to n, if you have a sequence of numbers from 0 to 2n, it means that you have n even number, n even number, n odd number. You can check it. So it means here the number value of k that we have here is 2 power n divided by 2. It is 2 power n minus 1. So this is the number of odd number that we have between 0 and 2 power n. So if I put capital N here, I will just say capital N over 2. You can just take an example. From 0 to 10, you are going to see that you have 5 odd number and you have 5 also even numbers. Now, Fn is measurable and it is positive. So Fn is a sequence of positive measurable functions. Yeah, Fn is a sequence of positive measurable functions. Now we have to check the monotonicity. Is Fn increase Fn increase or decrease, or is neither increase nor decrease? Maybe Fn does not increase and does not decrease, or maybe it is increased and or it is decreased. So we have to check. Now, what is Fn plus 1? Fn plus 1 of x is 1 if x is between k over 2n plus 1 and k plus 1 over 2n plus 1 and 0 otherwise. And you know that to compare two functions, because we like to compare Fn of x and Fn plus 1 of x, we need to have the same domain. So here the domain are not the same. Is it possible to find an intersection between these two domains? So to see how we are going to compare Fn of x and Fn plus 1. Now, so this is with k equal to 0, 1, 2, up to 2 power n, and k out, as you know. Now, what is Fn plus 1 minus Fn of x? Because you know that if this one is less than 0, it means that the sequence decrease. If this one is greater than 0, it means that the sequence increase. You know that there is a many way to study the monotonicity of a function or of a sequence. In high school, we were computing when you have a sequence un like this. If un plus y minus un is greater than 0, you are going to see that the sequence increase. If un plus 1 minus un is less than 0, you are going to see that the sequence decrease. So if un plus 1 minus un is equal to 0, you are going to see that you have a constant sequence. Is there a question? No, okay. Now, as I said, to compare two functions, you have to be sure that you are in the same domain. Now, we are not in the same domain. We have the domain. So if we take the first one, we have k over 2, and you have k plus 1 over 2n. And now we have k over 2n plus 1, and we have k plus 1 over 2n plus 1. If we take a line, like this, between k between n between so I think that we have maybe 1 over 2n plus 1 here, and you have maybe 1 over 2n here, because 1 over 2n plus 1 is less than 1 over 2n. Now, what is the interval? What is the interval k plus 1 over n like this? So we have maybe k this one here, and we have k this one here. That is what we have. Now, if we take k plus 1 of 2n plus, this is k plus 1, and this is k plus 1 of this. So this is our domain. This is our true domain. So what you can see that the intersection between is empty. The intersection between this one and this one is empty. So it means that we cannot talk anything about fn plus 1 and fn. We cannot subscribe. So we cannot do the difference fn plus 1 minus fn, because we don't have any point. There's any point between fn plus 1 and fn. So it means that the sequence is not increasing, and it's not decreasing. It does not exist. So fn is not increased, and then we cannot apply the Beppo theorem. But maybe we can compute the limit. We are going to try to see if we can compute this limit. So what is the integral of fn between 0 and 1? So you know that this is the integral of fn of x from k over 2 power n, k plus 1 over 2 power n of 1 dx plus 0 otherwise. So everywhere except in this interval, otherwise. So this is just kn plus 1 over 2 power n minus k over 2 power n, which is 1 over 2n. So that is the integral. Then the limit when n tends to plus infinity of this integral is just the limit of 1 over 2 power n, so which is 0, you know. So this one is the geometric sequence with the reason less than 1. So the ratio of the geometric sequence is between -1 and 1. So up. So if we raise it, if you raise it power n, the limit is 0. So we are done with the first subject related to functional analysis. So we are going to move to the second one, I think, since that we still have time. And I hope that you have understood everything very well and you are very happy.
For sure, we are happy.
Okay, nice. I'm happy to know that you are happy.
Yeah.
Now, what is the next? So the next is the subject of the 20th of January, 20th of January 2026. Okay. Functional analysis. So academy year 2024, 2025. But I don't understand why it is written the 20th of January 2026. I don't know why. So maybe let me write 20th of January 2025 instead of 2026. What is written here? So the first question is, so the instructions, only one sheet can be submitted. Write your surname first, and then your name and student number, so your matricular. Now, let omega a subset of Rg. So Rg contains omega. So be a measurable set, and let Fn, so a sequence of functions, so a sequence of measurable function from omega to R, be a sequence of measurable functions. So the first question is to define what is meant for the sequence Fn to converge almost everywhere to a function f. So one, let so let us define what means for the sequence Fn to converge almost everywhere to a function f from omega to R. Yeah, this concept, maybe I'm going to define it to give it definition with a concept in measure theory. Because converging almost everywhere, it means that there exists a set where this sequence does not converge and the measure of that set is zero. No. Fn converge almost everywhere to X, it means that there exists a set A in omega such that for all X that we take in A, the limit of Fn of X when n tends to plus infinity, such that maybe I will that such that Fn and the measure of A is 0. That is the meaning. So it means that where F does not converge is negligible. So you cannot take it into consideration. I hope that the definition is simple. Okay, now let us define the space LP omega and its norm. So we are going to define the space LP of omega. We are going to define its norm, and we are going to explain what means for Fn to converge in LP norm. So what is LP of omega? LP of omega is just the set of measurable functions such that LP of omega is the set of F from omega to R measurable such that the integral over omega of the absolute value of this power P dx is finite. I hope that you can see. If you cannot see, let me rewrite it here. Measurable. So it is the same thing. So I'm just afraid that you cannot see very well what is written up here, up there. So that is the set LP of omega. So it's the set of measurable functions such that this integral is finite. This integral over omega, as you can see. Now, what is the norm of this? So let F in LP of omega. What is the norm of F? The norm of F in LP of omega is the integral of the absolute value of F power P or the integral power 1 over P. That is the norm. That is why we used to write this. So the norm of the LP norm of F power P equal to this. So I hope that everything is clear. Now, we have to explain. Let us explain. Let us explain what means for a sequence of function fn to converge in LP norm. So what we call the convergence in LP norm. Okay. So let Fn in LP and F also in LP. Fn converge in LP norm to F if and only if and only if the norm, so the LP norm of this tend to 0, or the integral of this in omega of Fn of x minus f of x raised power p dx tend to 0 as n tend to plus infinity. So that is the notion of convergences in LP norm. So I hope that it is good for you with these definitions. Now the third question. So let omega equal to r and consider the sequence of functions fn of x equal to the characteristic function of this where I hope that you know what means by characteristic function. I hope that this is not a mistake. Okay, I hope, because it is 0 here, but up it was 1. If and 0 otherwise, that is the meaning of this symbol. So there's another name of this characteristic function that it's like I forgot. Let me try to relocate. Characteristic function, the second name.
Indicator.
Ah, nice. Indicator function. So that is it. Now, the first question is, does Fn converge almost everywhere? If so, determine the limit functions of F. So let us check. Let us check if Fn converge almost everywhere. What can be the limit of Fn? What you can say that is the limit of Fn of x when n tends to plus infinity base of what is given. So the limit of this characteristic function or this indicator function when n tends to plus infinity. And what is this? This is 1 if x belongs to 1. Is it true? I don't think that this is true. Is it true this set, this interval, according to you? I hope that I can see very well. I don't know if it is a mistake or not. I don't know if you have. Do you have the subject? Do you have it? I don't know if you have it. Maybe I'm the one who's not seeing very well. Maybe you don't understand what I'm saying, that this interval is false because this one is less than this one. I don't know if the function is well defined. What do you think? I hope that you're not just listening like it was, I don't know, it was a meeting with the Peter. In the church, according to you, is it true? What is given? The sheet.
We think it's not true. Since the n is positive number, 1 is bigger than 1 negative 1 over n.
Yeah.
Yeah.
I don't know. Maybe it was 0. Maybe let us put 0. I don't know. Maybe it was.
I think it was I think it's a mistake.
Yeah. Let us put 0. So we don't longer need this. Okay. Just a little precision. Yeah. This is for P finite. Yeah. P should be finite. Because when P equal to plus infinity, we have what we call the essential supremum. Maybe I hope that you have seen it. This is just for finite P, where we are going to talk about L infinity. Now, so when n tends to plus infinity, what are we going to have here? As we see this interval, is this a decreasing sequence? Is it a decreasing sequence of set, or is it an increasing sequence of set? If I take A, because you have to check it. If I take A equal to this,
I thought we're starting with 0.
AN, sorry. If I take AN equal to this, AN plus 1 is 1 over N plus 1. So, what do we know? We know that if I take my line as usual, you have to compare both of them.
Please, are you still using 1 or 0?
Oh, it's 0, sorry. I forgot to change. 0, 0. Now what I know is that this one is less than this. So even this one is less than this. So it means that AN is included in AN plus 1. So we have a decreasing sequence. It means that when we are going to take the limit of this, it will be the intersection of, so it will be the intersection of this. Which is equal to 0, 1. Then it means that the limit of Fn, if this one was, if this was an increasing sequence, is it an increasing or decreasing? It is an increasing, sorry. So normally we have to take the union of this. Now, I hope that the union of this interval is going to give this interval. Yes. You can check, you can just take for different value of n up to 0, 1. We are going to see that 0, 1 over 2, 0, 1 over 3, 0, 1 over, I don't know, all of them that are included in 0, 1. All these intervals are included in 0, 1. So the union of all these intervals is going to give 0, 1. Then this is 1 if x is in 0, 1. That is the limit of an. I have to precise it, which is the union of this, which is 0, 1. Let me write it normally. So an is included in an plus 1. So the limit of an on n tends to plus infinity is the union of this which is 0, 1. Then the limit of the indicator, the limit of fn of x, which is the indicator of what we know, will be equal to 1 if x is between 0 and 1 and 0 otherwise. So when you have this kind of function, this kind of sequence, where the interval is also a sequence, so you have to be very careful, and you have to proceed as I did. So you have to check the monotonicity of the sequence of interval. If it is increasing as here, you are going to take the union of everything. If it is decreasing, you are going to take the intersection. Now, what was the next question? For which value of P? For which values of P? In 0 plus infinity does Fn converge to F in LP of R? So this F is what? This F is the Pointwise limit. So the question is to know for which value of P this one converges to this. So f of x is the pointwise limit that we computed here. Then the pointwise limit is the limit that we obtain with the almost all convergence. Now, you know the definition. So what is the integral? What is the integral in R of fn of x minus fx power p dx? So that is what we have to compute. This is what? This is the integral in R. Is it in R? This is the integral in 0, 1 minus n of what? Of fn of x minus fx power p g dx. Which is 1 minus 1, which is equal to what? 0 for all p. So is there any condition on p here to have this, to compute this limit? I hope that you understand. Yeah, I hope that you understood why I moved from R to 0, 1 minus 1 over n. Because R here can be taken like the interval 0, 1 minus 1 over a union the remaining part, which is R minus that interval. And you know that the function f is equal to 1 year, and year is otherwise. So in R minus this, it is 0. So that is why the integral here in otherwise, the place that we used to call otherwise, the integral here is 0, and the integral here is 1. And it's the same thing for the sequence, and the same thing for the function. Then it means that for all p, Fn converges to F, because we found out that this integral equal to 0. Don't forget that by the end of the day, you have to get that this one is equal to 0, because you can compute this integral, but at the end you have maybe 1 or -1 or half, I don't know. It means it doesn't converge. Convergence in LP, it means that the limit of this integral when n tends to plus infinity should give 0. So this integral itself is 0. So the limit is 0 when n tends to plus infinity. But if you don't have 0 here, you have to be very careful. If you don't have 0 here, you have to be very careful. It means that it doesn't converge in LP. But yeah, everything is simple. So that is why we have the LP convergence for every P, for all P. I don't know if there is a question or not. Is there any question related to this? If there is no question, we are going to move to the next question, which is the second question, and it is the last question, and maybe the last part of the day. Maybe we are going to plan a new session, or to schedule a new date to do the remaining subjects. No question. It means that you have understood everything very well. Nice. The second question of this subject is, you have C01, so the set of continuous function. So let C of 01 denote the space of continuous function from 01 to R. The space of continuous functions F from 01 to R. Equipped with the infinitum, with the supremum norm. The supremum norm is the uniform norm, as we know. So let me write it very well in red, because even during the exam, you can be asked to give this. And we can also say in this case that it is the maximum of this, because 01 is compact. It's a compact domain, and F is continuous. It means that we are going to attend the maximum and the infimum. So the supremum is the max in this case, because we are in a compact domain. what is the first question? State the Arzela-Ascoli theorem. Okay, let us state the Arzela-Ascoli theorem. Let us state the Arzela. So this term is very fantastic. So you have to memorize it and to understand how to use it and to know the purpose of using this theorem. Okay. So let KG be a compact metric space. And it is also very good to know what is a definition of a metric space, and to know also what is the definition of a metric, and to know also what is the compactness. So what's the definition of being compact? Yes. Let KG be a compact metric space. Let this F a family of continuous function on K. Then this family of function is compact. Then K is compact in CK equip or involve with this supremum norm or the uniform norm. If and only if and only if F is cross bounded and equicontinuous. Bounded and equicontinuous. So this theorem has a lot of concepts that you have to know. You have to know what means to be a bounded set. You have to know what means to be a closed set. You have to know what means to be equicontinuous. Maybe I'm going to give a definition to recall what means equicontinuous. So this one is not part of the theorem again. The theorem stop here. So what is written in right now is just a recall. F is said to be equicontinuous. To be equicontinuous if for all x and y, maybe if our initial domain is capital X, I'm going to say for all x and y in X, and for all epsilon positive, such that for all epsilon positive, there exists a delta positive, such that the distance between X and Y. So this one is the distance on X. I can write the distance on X. So you have XD, a metric space. So this is the case that we have XD, which is a metric space. So XD is a metric space. XD is a metric space. So F is said to be equicontinuous if for all x and y that we take in X, and for all epsilon positive, there exists delta positive, such that the distance between X and Y is less than delta. Then the distance Now that this is another distance.
Mm.
The distance between fx and fy is less than epsilon for all f in this calligraphy f in this family of function. So in the beginning, let me also write something. We also have y gy a metric space. Yeah, we can take it like this. It could be that this g and gy they are the same. So depending on how the problem is defined. So this is just the definition of a key continuity. So when you have a function, a family of function is a key continuous if the family satisfies this. So for all the functions that you have, you can have this. And this Arzela-Ascoli theorem can be defined, can be stated in another way. We can remove this one. We can remove this concept of closeness. And we are going to say that F is precompact in this if F is bounded and a key continuous. So we are going to say precompact or relatively compact. So we can remove the closeness. So, and we are going to now say precompact or relative compact. So there is a many way to define it. So this one is the general one. But if the closeness is not ensured, so we are just going to conclude that your capital or your calligraphic F is precompact or relative compact. Or to be again relative compact, it means that the closure of the set is compact. So I think that you know a lot of things related to this. Yeah, this Ascoli Arzela theorem takes a lot of notions. So don't be surprised that you can have an exercise that the question is to show that you have F is precompact and you have to use the Ascoli Arzela theorem. So the first thing that you have to think is to think about the Ascoli Arzela theorem. And you have to know that you just have to show that it is bounded and a key continuous. That's all. Bounded, it means that you take a function and you show that the norm of the function is finite. That is all bounded. So you take just a function. You show that the infimum, the supremum norm is finite. So the uniform norm of the function or the supremum norm is finite. That is what we mean by being bounded. Okay, nice. What is the next question? Okay, let Fn a sequence of this. Let Fn so this one is a sequence of function of continuous function in 0, 1. Be defined by Fn of x is equal to sine of nx. That is what it is defined. Now, let us show that this family of functions is relatively compact. So relatively compact is the same thing like pre-compact. So don't be confused. It is the same thing. So just different words. in C01. Now, as I said, the Ascoli-Arzela said F is closed, bounded, and equicontinuous. Though, so then F is compact. But now we are talking about pre-compact. So you have to remove the closeness. So what we are going to show that is just that F is bounded and equicontinuous. And we are going to conclude. So it is very easy. So pre-compact, it is very nice. And in most of the case, sometimes the question will be to know if the set is pre-compact or the set is not pre-compact. So that in that case, you have to check. You don't know. So the question is not to show that it is compact, it is pre-compact, but it you are asked, is it pre-compact? Now, most of the most of the case, what does not work in that case is the equicontinuity. So in that case, you have to find a counter example to show that your family of function is not equicontinuous. If it is not equicontinuous, and it's the best thing to check because the boundedness will be always sure. I don't, it is like it's always sure, but you also have to check it. And if you are lucky, maybe you are not going to have the boundedness, which is very easy to see sometimes. So now our preoccupation is to show that this set is relative compact. So now what can we say? No, let Fn in this set. What is the absolute value of Fn of x? The absolute value of Fn of x is the absolute value of this function. And this is just the absolute value of this. So when you are here, you can do as you want. I said that you can do as you want, depending on the way that you want to do. Now I can just say this one is less than nx over n squared plus 1. But if you don't want to solve far, you can just say this everything here is less than 1 because you have 1 over n plus 1, which is less than 1. You have also the absolute value of sine x, which is also less than 1. But yeah, I don't want to do that. I want to do some little mathematics. What we know that this one. Why? Because sine function is a Lipschitz continuous function. So we have this. Since that the sine function it is a Lipschitz continuous function. So I want to do it like that because I want to call some mathematical notions that can be useful for you later. I don't know why. I don't want to do it in the simpler way to say that this one is directly less than 1. And you have the result. So we are going to see that the norm of f is less than plus infinity. So f is the family f is bounded. Now this is also less than x, since that this one is less than 1. Now, why do I want to have x here? Because I would like to take the supremum in both sides. The supremum when x is between 0 and 1, and the supremum, yeah. This one on the left hand side, this supremum is the norm, is the infinite, the supremum norm of Fn, and the supremum of x between 0 and 1 is 1. So then F is bounded. That is all. And as I said, it was possible to have this less than 1 since here. Now we have to check the AK continuity. AK continuity. So let x, y in 0, 1 and epsilon positive. So we need to find delta positive such that the distance between x and y, we are in R, so the distance between x and y, dxy, is x minus y less than delta, imply the distance between fx and fy less than epsilon. We are in R, so the distance here is just the absolute value in R. So the distance here is just the absolute value. And you have to be careful. It's not everywhere the same thing. If you're not in R, or if you have a particular distance or metric which is defined, you have to be very careful. So that is what we want to do. Now, what is the absolute value of fx minus fy? So this is the absolute value of sine nx minus sine ny. So I can put this term out, and I will have sine nx minus sine ny. And you know that the sine function is it is a Lipschitz continuous function. So this one is nx minus ny. So which is again n, it is less, sorry. So it is again times x minus y. And this is less than this, since that n over n squared plus 1 is less than 1. And don't forget that we would like to have this quantity less than epsilon. So to have this quantity less than epsilon, this quantity should be less than epsilon. So this one is less than epsilon. And we were looking for delta such that this one is less than delta. Then it means that delta is equal to epsilon. So by taking delta equal to epsilon, then f is AK continuous. Then f is continuous. So as f is bounded and a key continuous. Zero one 01 R, what am I going to say? 01 with this metric. It's a compact metric space. Then by Arzela-Ascoli, F is relatively compact. So I don't know if you have questions, you can ask it. If not, it was a pleasure to work with you today, and you can just try to plan another day where when you are free. So I don't know if there any misunderstanding somewhere. If it is the case, you can just let me know and we can explain it again. If not, I would like to thank you and I'm going to close the session.
Yo, thank you. We appreciate you.
Okay, thank you, Justin.
Yeah.
So Etienne doesn't have any question. Etienne.
I am okay, bro. Thank you so much.
Okay, nice. Okay, I mean, Belgian, I hope that Belgian is that too. They are happy. If women are happy, it means that even men are happy.
Yeah.
Okay, nice. So see you for the next session. We can discuss in the group. So I'm going to share the PDF and I'm going to put also this one on my special YouTube page, and I'm going to share the link with you so you can watch as well as you want. And you can also share the link with people who would like to have any idea about functionalizing and about these exercises.